I'm going to attempt to make all 4 presentations on Oak Ridge specifically. And since we've heard a lot already about the choosing of the site, I'm not going to focus on that, but mostly on the building project itself and how everything started being hit from the ground.
We could change the plate.
So just giving a really quick timeline overview of the choosing of all the sites for the Manhattan project. The Tennessee site was chosen first as a pilot site, actually 76 years ago yesterday. So it was sort of fun. General Groves chose this site in 1942, and the next site chosen was Los Alamos, New Mexico, just a couple months later. And then Oppenheimer was chosen as the laboratory director. And then I thought it was rather interesting that all these things are going to come into place before Roosevelt had actually finalized the plans and approved them for the buildings. So I appreciated that General Groves was already on the call before. And then the last site chosen was Hanford, Washington in 1943. And then just a quick overview of the construction in Oak Ridge. In 1943, February, they began construction of Y12 and they broke ground for X10. And then almost a year after it was chosen, they began construction of K25. And then in June of 1944, another full year later, they began construction of X. Another thing I forgotten was that Oak Ridge is not the original name of the town. It was originally called Site X by the government, and then Clinton Engineer Works by who lived there after the engineering company that had a lot to do with the building of the town. It wasn't called Oak Ridge until after. So it was 60,000 acres, and we already learned about how it was chosen. This displaced approximately 3,000 residents, which was sad, of course, but it also provided a lot of jobs for a lot of people in the surrounding community and from across the nation. A lot of people moved. So it grew to be about 75,000 residents in approximately. So here's an example of an eviction notice that I found. So the government is allowed to take private property in the event of war, but they are supposed to pay for the land they possess. But oftentimes the value given to the homeowners is a lot less than market value. So this, I want to read it because my mom thought this is so interesting. So they received this on November 11th, but they had to move out by December 1st. So the War Department intends to take possession of your farm December 1st, 1942. It will be necessary for you to move not later than that date. In order to pay you quickly, the money for your property will be placed in the United States court and not CC. The court will permit you to withdraw a substantial part of this money without waiting. This may be done without impairing your right to contest the value fixed on your property by the War Department. It is expected that your money will be put in court within 10 days, and as soon as you're notified, it is suggested you get in touch with the United States Attorney to find out how much you've drawn. Your full cooperation will be material aid to the war effort. And this one specifically, there is a storyline behind Farley Brady. So she was actually given this land by her stepfather, farm. Her stepfather was John Hendricks, and it has a funny, sad but funny story. His infant daughter died, and his wife left him, so he sort of went crazy for a period of time, living out in the woods and claiming that he was having visions. And one of them was that there was going to be a war unlike anyone had ever seen, and it would include building factories using large machines in a small area. Everyone thought he was crazy, but I think it was only like 20 years later, something like that, that all this started coming to pass. So that was her stepfather, and she inherited his land.
Yeah, her stepfather. So the Hendricks story, he got driven into despair because his wife and took the kids and moved to Arkansas or something, right? So then he married somebody else with a child. And that's who this person. Okay.
Here's an example of flat top houses. These were prefab homes. And as shown in this picture, they were small enough to was not very large. They were, so the B1 home was 576 square feet, so not very large. That included 2 bedrooms, a bath, a kitchen, pantry, and a living room. And so these were not meant to be permanent, but if you visit the American Museum of Science and Engineering, you can see a small one that's there. And is it completely intact?
It is intact.
Okay, I've seen it before. You can actually go inside the house. It's really neat. But it's sort of crazy to think that that's what people lived in for several years and sometimes for the rest of their lives. So Rome wasn't built in a day, but the bridge was very close to that. Colonel Nichols was only 34. He was appointed to the district engineer. And he hired Skidmore, Owings and Merrill, which was almost unknown company to be the architecture firm for building Bow Bridge, and now they're a ginormous company. This is their website. It sounds like things that they've taken part in. But this small company was given the instructions to initiate the nomenclature of the streets and basically build the suburbia that Oak Ridge was going to become. I thought it was interesting. Oppenheimer requested for Mulkeys like front porches and wooden floors because he wanted academics to be excited about moving there. But the Skidmore, Owings and Merrill said that wasn't going to be possible for the amount of homes that they had to build. So they tried to have elements of homey comfort, but it was just impossible to do that for the sheer amount of work that had to be done. At the height of construction, one house was built every 30 minutes, average of 17 houses a day over the time period of building. On a more personal note, my great-grandfather worked on a vineyard project. After he graduated from high school, before he got married, he said he would walk to work, and then on the way home, there would be an entire new community built that was not there when he left for work that morning. So I had no idea what was going on, but they were in a hurry. Also very interesting was Oak Ridge was pioneering in the construction industry. A lot of the models that we have now for neighborhoods are built on the Oak Ridge model of small areas of homes and little streets that are like communities within a larger community. There was also a variety of homes. Hutments were more temporary. They could be built from plywood and other scraps. Multi-family dwellings, single-family homes, which can be known as like alphabet houses. So type A home was the smallest. Type B was the one that's shown before. Type C was an L-shape, and type D is actually the original floor plan for the modern style ranch home.
Oh, but you forgot one.
Okay.
E.
E, okay.
When I was a graduate student, my first apartment as a married graduate student was E2. And that was this is an E1, so it's a 1-bedroom. E1 on this side. And this is a 2-4, 2-bedroom. E2. So I lived in an E2.
There are still some of those standing in Oak Ridge.
I know when I lived there, it was bad shape then in 1966. It's still standing. It was
Cheapest thing we could get. Yes.
And so I found these statistics, which I thought was interesting, that a farming community that had just family homes and farms turned out to be a community with 300 miles of roads, 55 miles of railroad tracks, 10 schools, 7 theaters, 70 restaurants and cafes, 13 supermarkets, 9,400 both library, church services for 70 denominations. So a lot of people were born here and would not have known any different from what it looked like a couple of years prior.
So when was this count?
I think this was towards the end of the war.
Oh, already during the war. There were 7 theaters. Oh, okay.
And they went 24 hours in that.
There are not that many in Oak Ridge now.
No, well, there is. If you count all of them in that one building. There are.
True.
That's my last slide.
Thank you, Eva. Questions or comments?
Very good.
So you,
Were the E-houses maybe not built till later?
I don't know.
No, they were built during the Manhattan Project. They were apartments.
Right, so they were in the other category that you had.
Yeah.
And there were dormitories, any dormitories, H-shaped dormitories. So 75,000 people living there in August of 1940.
I lived in one in the E2,
Did
in
you?
East Tennessee.
You lived in E2?
On Tennessee?
Yeah.
In an E2?
You
Yeah.
did that, you forgot.
I forgot. Wow. On Tennessee.
East
That's
Tennessee.
near where I was, California.
Yeah, yeah.
Oh,
Right by
It
the
is.
barber shop,
California's just a little east of
across from the school grounds, right by the barber shop,
it. Yeah,
this shopping mall.
right.
Yeah, and the E2 we lived in was right, California. It's the turnpike. At that time, there was a Dairy Queen right in front of the E2. And Tina was pregnant during that time, and that was a big temptation. If you live right behind a Dairy Queen when you're pregnant.
My first visit to the museum when I got here in '82, I was looking through the history of Oak Ridge section and came across an ID card from one of the residents back in the war, and it was the address I was living at that time,
Oh.
on Georgia Avenue.
Yeah.
What letter was it?
They called it Model 35.
There are a lot more distinctions than just the alphabet houses. If you look, there were models of variations of the basic alphabet.
This was a ranch style.
Yeah, they
and
call
was
it
a little bit larger than most of the others.
Very good, Eva. So you're going to proceed in your other talks about the history
I
of
want
Oak
to
Ridge.
focus on propaganda, or the signage, maybe not propaganda, but the signage.
Careful how you use that word.
The,
That's a good thing.
Good. Yeah. So I want to start having each of you send me some answers each week, a little exercise to keep you up with the material. And Ray sent this link to the videos. Ray has produced all of these videos about the history of Oak Ridge. And I'll send this out by email to you, the first assignment. The first assignment is by next week to watch this one. It's 26 minutes. And I just watched it while I was eating lunch at my desk and made up some questions, one of which Eva answered already. As you watch that, send me the answers, and it's really good. And so there's a set of these. And so that's one activity I want you to do. And I want to right now show one of the shorter clips. This is 6 minutes. Let's watch this one. So Ray Smith is the star of this production. Did you get an Emmy or Oscar or anything?
I have a couple of little statues where we've won some international film festivals.
You have?
I do.
Wow. Impressive. I knew you were a star, but I didn't know you were an international star. Okay, so let's watch this one. This is one that Ray produced about, there's E.O. Lawrence.
From modest and humble beginnings to secret mission to being one of America's best resources for new technology. These valleys in East Tennessee have a rich and diverse history. We want to honor those who came before us. We want to keep our place in history alive by revealing the secrets of our hidden past.
I don't know how to make it bigger.
I think the top left.
the like
Here?
two arrows of the
It
actual.
was the biggest secret, not even the biggest.
Oh, yeah, yeah, yeah.
That one.
Oh,
In the early 1940s, thousands of people from all over the United States poured into a quiet farming valley in East Tennessee. And 3 sites mysteriously named White Willow, X-10, and K-25 began work to end the deadliest global conflict in human history, World War II. Well, the White Well site, it all started right here in Building 9731, known at the time as the pilot facility. In March of 1943, the largest magnets in the world were installed here. They were used for a special separation effort to get an isotope that was really needed for the war. Caviotron is what it was called. And this is the first of many installed here at White Well. Now, just what is a caviotron? Well, it's a mass spectrometer, basically a giant electromagnetic device for separating isotopes. Nobel Prize winning physicist Ernest Lawrence invented the caviotron in California. It's named after the electron magnet cyclotron at the University of California, Cal-U-COM. Here's how it works. A beam of uranium ions passes between the poles of the magnet, causing the ions to bend. They are split into different streams according to their mass, with the heavier ions making a larger arc, and the lighter ones making a slightly smaller arc. The small amount of the rare isotope uranium-235 was separated from the much larger amount of uranium-238 in natural uranium. The caviotron worked at the laboratory level, but would it work for large-scale production? To find out, the caviotrons here in Building 9731 began running in early 1943. They were used throughout the war to make improvements to the other caviotron production units required to separate enough uranium-235 for the war. Lawrence journeyed here many times to check on how well the caviotrons were working. On one occasion, he was very ill, but he caused quite a bit of consternation on the part of one of the scientists.
We were running one night and very contentedly receiving uranium-235 into the collector pockets, and not a lot of sparking, not a lot of interruption. And Theo Lawrence came in and he said, "This is the best that will do?" And he sat down at the controls and he started adjusting the voltage, adjusting the temperature of the oven to get more uranium out. And he increased that production tremendously. But at the same time, a lot of fireworks were going on inside the vacuum chamber. In about 5 minutes, everything literally blew up inside the thing.
Lawrence's idea worked very well, even though it caused problems with its first attempt. The improvements were quickly implemented in the production caviotron. Working around the clock, they produced enough uranium-235 to supply the world's first atomic bomb ever used in war, Little War. It exploded over Hiroshima, Japan on August 6, 1945. Japan surrendered a few days later. With the end of World War II, Blackwell's first mission was completed, but there were many more to come.
so you have a whole set of those on this website. Okay, so another one on that website is this one here. I'll send out that link to you. I'd like for you to watch this one before next class, 26 minutes. Goes over some of the stuff that Eva talked about, but I think it's neat just to understand more about the history. And so, and I'll send you a little set of questions to answer.
I have a quick question on that.
Yes.
Was that black and white footage of warrants in the lab, was that real? Was that like you
No,
actually
that-
during this visit?
Yes, that footage during the, Lawrence, when we talk about Lawrence's visit,
Yeah.
that was actually footage out in California at Berkeley at the 62-inch cyclotron. We didn't have footage of Lawrence in Lafayette.
That's what I was thinking, I was like, that's really weird that they would video it secret.
And the footage of Dr. Kine was made by the Smithsonian when they did oral history interviews in the 80s. So we just picked. You bet. That's the beauty of filmmaking, you know. You can piece them together, illustrate your point.
By the way, these are some of my books I have about some of the people you're talking about. You can come up and borrow some of my books about Oppenheimer or, by the way, John, I found one I have on Heisenberg. You may want to borrow that. Okay, so let's continue the historical survey. By the way, for those of you listening by Zoom, we will not have class on Tuesday of next week. I have to be out of town. So then we'll resume next Thursday. All right, so let me get this set up here. Of course, a lot was happening by 1930 and 1940. The US government was slow to act. Remember, the seminal experiment was done in Berlin in December of 38. Many studies at different places started happening after that. Much research, much of it published in the open literature. Finally, the US, under prodding by Einstein and Szilard and the Hungarians, basically, the Hungarian physicists that were in this country, prodded the US government, and so a uranium committee was formed in early 1940. But it was all moving very slowly. Moving more rapidly in Germany. It was even moving far more rapidly in England, that I want to tell you about. Finally, the uranium committee, military leaders were involved in this. That's one reason it moved so slowly, because they were skeptical that you could invent on such a rapid time scale a new weapon that would impact this war. We were not in this war yet, but the war in Europe was getting more and more intense. And the US was, leaders of the US were dragging their feet. But finally, $6,000 was appropriated to do a measurement. It was the idea of Fermi, of Szilard, and others, that you could maybe have a chain reaction. But you needed a moderator to slow down the neutrons from fission to allow other uranium nuclei to fission. And the question is, would graphite absorb too many neutrons and not function, therefore, as a moderator? So they did appropriate the $6,000, but that was about it. That's about all the uranium committee did at that time. But that enabled Fermi and Szilard working at Columbia to do an experiment to show that you could make a chain reaction using natural uranium. By this time, there was a lot of thought, and Bohr was the leader of that it was uranium-235 that was the fissionable isotope of uranium. But the idea still by Fermi was to build a pile reactor, but then you need a moderator. And so Fermi got the $6,000, got some pure graphite, and they succeeded in measuring the neutron absorption properties of graphite and found it to be small. It was 1,000 times smaller than the geometric cross section. Remember that term. And if a nucleus has this size, and a neutron comes zipping in, then the geometric cross section just says if the neutron hits that nucleus, it's going to get absorbed. And that's what they were assuming would happen with uranium. When a slow neutron hits uranium, it's going to get absorbed and cause fission. But luckily, when Fermi and Szilard did this measurement, they found that the neutron absorption cross section for graphite, for carbon, was 1,000 times smaller. That's good. Therefore, it could work as a moderator. And so that was good for trying to build eventually Fermi's reactor, but of course it didn't have any meaning as far as building a bomb. The Brits were very much focused on whether this could be harnessed to build a bomb. The British government couldn't understand why U.S. was moving so slowly. And so someone from the British government came to U.S. and did inquiries as to the status of the Uranium Committee. They were quite dismayed to learn that A, it was moving slowly, and B, the Uranium Committee was not talking about trying to build a bomb. They were talking about how you could build a reactor. Thus the importance of graphite as a moderator. Headed in a different direction entirely. Of course, the Brits were being attacked by the Germans by air, so they really felt the urgency. Vannevar Bush. Bush was important in this time, very important in this time. He was an engineer. He was the vice president at MIT. In 1939, he became president of the Carnegie Institution of Washington. He knew what was happening in Europe. Hitler was trying to take over all of Europe. He saw war coming for the US. We'd have to get into it at a certain point. And he knew, being an engineer, that this would depend on technology advancements. He went to the president and proposed the formation of the National Defense Research Council, NDRC, a body of including scientists, engineers, and military that would then report directly to the president. So if the outcome of this war in Europe were to be determined anytime soon, it would probably depend on technology advancements. And that's what this new council would take care of. It was actually in parallel to the military. The Uranium Committee had military people on it, and so it was slowed down by military people saying, we've got enough weapons. It will take too long to develop a new weapon. This is a waste of our time and money at this crucial time. And so the president agreed to do that. June 12, 1940, Vannevar Bush was the chair of this. He became famous later after the war. He was the guy who ran the National Science Foundation. So he has had a big impact on science in the US, starting with his inventing and chairing the National Defense Research Council. And of course, I told you about this last time, that at the same time, in spring of 1940, Hitler had occupied Norway. Norwegians had put up some resistance. Hitler had marched to Denmark. He needed the farm products from Denmark. He needed heavy water, for example, from Norway. This led to the demise of Chamberlain, especially after Hitler marched then into Holland and Belgium. Holland and Netherlands is the same. I wrote that too quickly, of course. When he marched into the flatlands in Europe, then they invaded France. Hitler intended to invade England after that. Neville Chamberlain was the Prime Minister of England who said that Hitler only really wanted to get his hands on the German-speaking parts of Czechoslovakia, and we'll stop there. Well, Chamberlain was wrong. So Chamberlain lost his job as Prime Minister. That's when Winston Churchill took over. Then Italy invaded France. Italy declared war on France and the UK. France surrendered. France was divided up into different parts. And by August, there were aerial attacks on Britain, the Battle of Britain. And that was an intense 6 months. The Blitz, as the Brits call it, where Germans were bombarding England starting mid-August every night with a lot of bombs to try and weaken the population. The intent originally was for the Germans to attack airfields and industrial sites, military sites in England. And the Brits were attacking correspondingly military sites in Germany by air. Then a mistake was made where some German aircraft dropped bombs on London at night by mistake. And then that escalated the conflict. The Brits then attacked, dropped bombs on Berlin, and then all hell broke loose. And then the Germans started dumping 200 tons of bombs every night on London from September to May. That's the Blitz. It's amazing that England was able to withstand that terrible period over that. Yeah.
Is this when they would send their children out on the other side of the safer?
Yes, yes. One of my good friends here, he's now retired, David Pegg, was on the physics faculty for decades. He joined the faculty about the time I did in the early 70s. He grew up in London when this happened. He's a little bit older. I was born in 44. David was born probably in 39. And so they did that. He was sent to Cornwall. His mother took him to Cornwall, out on the west coast of England. But a lot of people left London because of this bombardment. Absolutely. The Germans were certainly, under the leadership of Werner Heisenberg, were working on their atomic bomb project. You know, when they took Belgium, they then had control over uranium mines in the Belgian Congo. And so that they had a source of 60 tons of uranium ore that they could do their experiments with. At the Kaiser Wilhelm Institute in Berlin, Heisenberg established a building to do work on uranium. And same thing that Fermi and Szilard were doing in Colombia, trying to see if you could have a chain reaction to build a reactor. He called it the virus house to keep people away from it, keep them frightened. They don't want to go close to this building. There weren't viruses there, but he just wanted to scare people. Germany did not have a cyclotron. That's important, as we've kind of discussed. Lawrence got a Nobel Prize for building the first cyclotron in Berkeley, and that became a crucial part of the American effort. There was a cyclotron in England at Liverpool University. So there came then experiments in those two countries for measuring the cross-section of the absorption of fast neutrons by uranium. The cyclotron for that, the best. Germany didn't have one, but after they took Paris, after they took France, and Paris was in their sector, then they had a cyclotron to do that same measurement like were being done in England and the US. At the Myers house, they did the same experiment, tried to do the same experiment as Fermi and Szilard were doing. Tried to see if graphite would work as a moderator. So they did that same experiment. Well, first they did the experiment to see if hydrogen worked, water, and they measured correctly that hydrogen absorbs too many neutrons, so it could not be a moderator. That meant theoretically they have to go to graphite or heavy water. Heavy water they didn't have. That's why they went after the hydroelectric plant outside of Oslo that made heavy water as a byproduct, making ammonia for fertilizer. Or graphite would be moderated. That's where Fermi and Szilard decided it would work. They asked Walter Botha, a physicist in Heidelberg, to do the same experiment as Fermi and Szilard. Would graphite work, or would it absorb too many neutrons to be a moderator in this eventual reactor? Walter Botha was a good physicist. He had been abused some in the mid-30s because he was not climbing on the Nazi bandwagon fast enough. Still, he was working. He was not Jewish, but his result was wrong. He got a cross-section 2 or 3 times higher than Fermi found in their experiments in Columbia. So, they found that Fermi found that the cross-section was 1,000 times smaller than the geometric cross-section. So graphite wouldn't work. Walter Botha concluded that it would not work. He got a result that was 2 or 3 times higher than what Fermi got. That was probably an honest mistake. There's no evidence that he was trying to slow down the Nazi train from making an atomic bomb. He probably made a mistake, or he had graphite that was not pure. It's not too uncommon to have graphite contaminated by boron. Boron has a large probability of absorbing neutrons. So it probably was that he had contaminated graphite, but he got the wrong answer. So that forced the focus on heavy water, since Walter Botha said the graphite would not work, it would absorb too many neutrons. And that's why they had to go to the plant, the hydro plant outside of Oslo, to get heavy water for their atomic bomb project. The Japanese also were working on this. The Japanese took Korea and Burma. Therefore, Japanese had a source of uranium, more than what they had in the ground in Japan. They appointed a physicist, Nishina, who had worked with Bohr in Copenhagen in the 1930s, so he knew about nuclei. He was a nuclear physicist. He read the literature, he knew about this fission debate going on. They built a small cyclotron at Riken in Tokyo. That's now a big nuclear physics lab, Riken, but it was a small lab then. And he also had contact with Ernst Lawrence, and so Nishina got plans for Lawrence's 60-inch cyclotron and built a small cyclotron in Tokyo at Riken. And he started doing the same thing, bombarding uranium with neutrons using the cyclotron. That was yielding results, and so in spring of 1941, the Japanese authorized an atomic bomb project. And a few people began to think about building a bomb perhaps with an unknown element beyond uranium. And I want to tell you that story. You see, now we know, after these experiments, now we know that, of course, you can absorb big neutrons, they'll get absorbed by the main isotope of natural uranium. And uranium-239 is not fission, but it has beta decay to neptunium-239. This was not known at that time, in 1940. Gives off electron and neutrino, the half-life of 23 minutes. And then that decays to plutonium-239, we now know, by beta decay, half-life of 2 days. Well, these activities, those half-lives had been seen when Fermi did his experiments in Rome in the mid-30s, when Hahn and Strassmann did their experiments, or Curie and her husband Joliot did their experiments in Paris. They saw activities like this, but they attributed it to something else. Now we know this is the case, but in 1939, this was not known and this was not known. But two people at Berkeley, Macmillan and Abelson, started experiments to see if you do make something beyond uranium. By this time, people bored said it's uranium-235 is fission, but what if neutrons get absorbed on uranium-238? What happens? Well, that's the experiments they mounted in Berkeley in late 1939. And they did different experiments where they hit neutrons on uranium-238 and did different measurements, looked at the fission fragments, putting in foils, having a source of neutrons, shield of uranium-238, thin target, put in a stopper foil to catch what you're making, take that off and count it, do some root metric chemistry on it. And in some long experiments, they found that this thing with a 2.3-day half-life was not a fission fragment. It was not something like barium or lanthanum, something half the mass of uranium. That it had the chemistry and the characteristics of something beyond uranium. So by May of 1940, they published a paper on the discovery of element 93 in these experiments. They were seeing this half-life. They attributed it to element 93. So they were seeing this decay, not knowing what it was exactly. And this is an important step. They suggested that this element be neptunium. You know, uranium is named after the planet Uranus. Next out after Uranus is Neptune. Next out after Neptune is Pluto. So that's why these elements are named that way by planets in our solar system. So that was a big step, May of 1940, that there does exist an element beyond uranium. Glenn Seaborg was a young chemist at Berkeley. He did his PhD in 1937 at Berkeley. He came from Minnesota, from Swedish stock, and after those experiments I just described, he started working hard on what happens when, if you make neptunium, what does it decay to? Uranium, neptunium would be element 93, but it then must beta decay to element 94. What is it? Can you isolate it? What's its chemistry? Does it fission? Does it beta decay? Many questions. So that's what Glenn Seaborg worked on. He had a young student named Art Wall, who then was a great nuclear chemist at MIT into the 70s, 80s. And Emilio Segre came from Fermi's lab in Rome. He got out of fascist Italy, and they started using Lorenz's cyclotron, newly built cyclotron, to hit neutrons onto a kilogram of uranium oxide as a target, and then to try to chemically separate what you produce, to chemically separate this new neptunium, element 93. then they could, if they could separate that chemically, then they could study what it decays to. And they did a series of chemistry experiments. They were nuclear chemists. And finally, after some months of work, they isolated chemically 0.6 milligrams of element 94, which is the daughter of this 2.3 day radioactivity. Then they, once they isolated that small amount of element 94 for the first time, discovered by Seaborg, they then put it in the cyclotron and hit it with slow neutrons and showed that this new element fissions due to slow neutron impact. And so he got the Nobel Prize in 1951, along with Edwin Morrison, for the discovery of plutonium, element 94. So that was a big step forward. So you see, this opens up a whole new possibility that I've alluded to before. One way to build a bomb that the Brits are focused on is separating uranium-235 from uranium-238. It's only one of 140 atoms in nature. Uranium is the fissionable isotope. That's what Lawrence ended up doing with the calutrons at Y12. The other direction is to build a reactor where we have neutrons hitting uranium-238, making neptunium, which later becomes plutonium, and that could be the fissionable isotope for which you build a bomb. So now you've got two possible directions for building.
You know what the half-life of plutonium-239 is?
Well, it's 2.3. Oh, half-life.
Plutonium.
Yeah. Well, I forget. I should know that. I forget. Well, let's see. And it of course, it fissions, but it also does alpha decay. But I forget the half-life. Celia will figure that out. The Brits were stunned by the inactivity, the slow movement. What is it?
24,000.
24,000 years, right? So plutonium-239 is a half-life of 24,000 years. So once you make it, you got plenty of time to make it into bomb material. Another important person at this time was James Conant. He wrote one of these books that I bring it with me this time. He wrote his memoirs from this period. He was an organic chemist, got his PhD at Harvard. He was, some called him the best organic chemist in the country. He was a very ambitious guy. He became president of Harvard University at age 40 and served for 20 years as president of Harvard University, and really was responsible for turning Harvard University into one of the best research universities in the country, in the world. It was not before he took over. He and Vannevar Bush became the two leaders of the Manhattan Project, but he was also part of the National Defense Research Council in this crucial period. So Bush, who started the NSF, and Conant, who was president of Harvard, were two of the important people on the Uranium Committee and on this research council that reported to President Roosevelt. He visited London in 1941 to start communication with the parallel British committee called the Dizard Committee. That was the name of the guy that chaired it. He learned something about what was going on in England, about their thoughts, their directions. He met with a professor at Oxford, Frederick Linneman, who was head of one of the big nuclear physics laboratories in England. And he was the guy that brought Leo Szilard from the Hungarian Jew to Germany, and then he brought him to England. And Szilard was the guy always saying that a chain reaction is possible. You can build a bomb if you can find the nucleus and the isotope that fissions easily. So he had always been a guy pushing these concepts. And he convinced Lindemann that a bomb based upon uranium-235 was possible. And that because you can make a chain reaction with uranium-235. And so the Szilard committee was very focused on that. And they told Conant this story. But Conant and the Uranium Committee, or Conant and Bush, did not really take this seriously and did very little to act upon what was happening quickly in England. Ernest Lawrence played a very important role in this period. He was a young, brash physicist at Berkeley. Oppenheimer was at Berkeley, which is not a prestige university at that time, around 1940, and Lawrence was at Berkeley. Both played crucial roles in the Manhattan Project. Oppenheimer, of course, was the theoretical physicist that became head of the Manhattan Project. Lawrence was from South Dakota, went to college in South Dakota, got his PhD at Yale, and then joined the faculty at Berkeley at age 29. And he invented the cyclotron. Wrote the patent in 1934, got the Nobel Prize in 1935 for the cyclotron. And that was a crucial accelerator. It was so important in World War II and thereafter. And, just want you to understand for a moment how a cyclotron works. You see, one way to accelerate nuclear particles is in a linear device called a Van de Graaff accelerator, and these exist. The tall tower at Cornell has housed for 30 years, 40 years, a Van de Graaff accelerator. And that's a device where you have a way to make charged ions negative. Strip an electron off of something like lithium. It's got a positive charge, but it's missing an electron. You take it by a belt up to a terminal. This terminal sits at a high voltage. The charged particles get taken over to the dome. You've probably seen these. If you hold a grounded metal ball, you can have a spark jump from this high voltage terminal. Those charges have gone up, they repel each other, they go to the outside, the surface of a metal dome. You can have a spark jump across, you can have a grounded metal sphere. I used to do this with my kids in the physics department. You have one of these, it's down on this insulated platter, put your hand on this, and your hair stands up. Because the charged particles want to escape, and they get to the ends of your body, and your hair stands up. It's safe. So that's one type of accelerator. But you couldn't get very much energy in those days from a Van de Graaff accelerator. And so Lawrence invented a cyclotron. Here you make charged particles in the middle, and then the charged particles go in circular orbits, held in circular orbits by a magnetic field in this direction. And the critical thing is that you've got to change the polarity of the voltage. When a charged particles crosses from this point to this point, you want to accelerate it to give it energy. So this metal D, there's a metal thing above the path of the charged particles that has, for example, a positive voltage. That negative ion gets accelerated from here to here toward this positive voltage because it's a negative ion, unlike charges attract. Then it goes into a higher orbit. By the time it gets to here, you then change the voltage so that now this is positive and this is negative. So that ion then gets repelled from the positive voltage and attract it to the negative. So this is what he invented. You got to flip the electric field of these two metal Ds twice every orbit of the spiraling positively charged nucleus. And it works. All the orbits are isochronous. That means as they come around, low energy ones at small orbit, they spiral outward. Higher energy ones in the bigger orbit, they all hit this gap at the same time. The orbits are isochronous. So it takes the same time to travel from here to here, whether you're in a high energy large orbit or in a small low energy orbit. That's the physics that makes this work. And Lawrence realized that, and he built this device. So you have the voltage on these Ds, this one, flipping back and forth at radio frequencies, causing all these particles to step, hit the D, accelerate, go to a higher orbit, and therefore accelerate charged particles to a much higher energy than anyone had been able to do before. And that's what he got his Nobel Prize for in 1939. So once he invented that, the Japanese built one like that. The French, the Brits at Liverpool, to try to understand the behavior of uranium or plutonium or whatever with neutron bombardment, and you use charged particles from a cyclotron to hit a foil, beryllium foil, to make neutrons of a higher energy than could be attained before. So that was important. The cyclotron at the radiation lab, as it was called then, now it's called Berkeley National Lab, up on the hill above University of California, Berkeley campus. That's where he built his first set of cyclotrons. And that enabled Seaborg Segre to understand neptunium and plutonium using beams from the cyclotron. Lawrence was a machine builder. He always wanted to build the next biggest cyclotron. And he had a grant of $1 million from the Rockefeller Foundation, a huge grant around 1940, to build a much bigger cyclotron, 184-inch cyclotron, to get higher energies. He then heard about that experiment in Minnesota that was mentioned in Ray's video, where he could also use the cyclotron concept to separate isotopes of uranium. That was what led to the calutrons, because you're bending charged particles in a circular orbit. You can separate them by their mass, 235 versus 238. So he was, as Lawrence was building a bigger cyclotron, he could realize he could take his old, smaller cyclotron and spiff it up and use it to perhaps do robust separation of uranium isotopes. He got impatient. He heard that the Brits were moving fast. He suspected the Germans were moving fast also in this direction. He saw that the Uranium Committee was doing nothing. They were dragging their feet. The military leaders on the committee were saying, we can't be distracted by new pie-in-the-sky weapons. We have to improve our existing weapons. And so he then knew Conant, the president of Carnegie Institution, and bugged him that the U.S. needed to step up its effort. He also went to MIT. President of MIT was then a guy named Carl Compton. So you had Conant, head of the Carnegie Institution. You had Bush, president of Harvard. You have a guy named, a physicist named Carl Compton, who was head of MIT. And he knew him, and he bugged him that the U.S. is not moving fast enough. We're going to lose. Vannevar Bush was kind of a control freak. He didn't like Lawrence, this Nobel laureate from Berkeley, criticizing the Uranium Committee. Told him to get in line and should not question the uranium committee. The chair was this guy from the National Bureau of Standards. He was a slow-moving, bureaucratic kind of person, and they didn't want to be distracted by all this uranium stuff. They were focused on radar, of course. At MIT, radar was being developed. There was no radar before World War II, and that was a crucial part of World War II. Not quite as impactful as the atomic bomb, but after that, very impactful. And so they were fully focused on developing radar for detection of aircraft. And so Lawrence's colleague had moved to MIT to work on radar development. He heard about, he was in England, and Mollett committee was their uranium committee working on what was possible. He heard about their quick efforts, their conclusion that you could build a bomb perhaps in as little as 3 years by enriching uranium in MAP-235, far ahead of where the US stood. So finally, when Bainbridge came back from England, he bugged Briggs, we talked to Bush, and they said, well, they've really got to do something. Can't, but it won't go away, this whole debate about uranium. So they asked the National Academy of Sciences. They asked Arthur Compton, who was the brother of Carl Compton. Carl Compton was the head of MIT. His brother was an esteemed nuclear physicist at Washington University, also Nobel laureate, discovered the Compton effect. So they set up a National Academy of Sciences committee to look at this uranium problem. That's Arthur Compton. He was on the cover of Time magazine in 1938, January of 38. He and Carl were both physicists. Their mother was a Mennonite. Their father was a Presbyterian minister. Very religious family. Arthur Compton was a very Nobel laureate physicist. Niels Bohr liked his physics, but when he was not talking physics, he became a preacher about religion. And so Bohr didn't like that part of Compton, but he respected him greatly. He had worked with, Arthur Compton had worked with Rutherford in England, and he became the chancellor of Washington University after World War II. He got the Nobel Prize in 1927. And his Nobel Prize, won't go into it, had to do with the fact that gamma rays or X-rays he'd worked with scattered off of something and changed their wavelength, increased the wavelength, and scattered off of a substance. And there's no way to understand that by classical physics if gamma rays, radiation were only waves. But if Einstein was right, that you could view X-rays and light also as particles, as photons, as quanta, as almost particle-like, then you could understand, if you observe experimentally, you could understand the Compton effect. And so that was then a verification of one of Einstein's papers from 1905. That light can be viewed as a particle or as a wave. They met twice in 1941. This is a committee of the National Academy of Sciences to look at the uranium problem. They wrote a 7-page report to the uranium committee. They pointed out that it was possible to, through uranium and fission, you could, for example, make a lot of radioactive material that you could drop from a plane to be a weapon. You could use uranium fission as a power source, which is what we do now. 90% of the electricity in the US comes from nuclear power reactors. Or this committee said you could build bombs, perhaps. of enriched uranium-235. That would take 4 years, at least. The report said that it was unlikely, therefore, that it would have an impact on this war that the U.S. would undoubtedly get into soon, but it could be a dominant weapon, important weapon for the future. So finally, Vannevar Bush took that report to the president, and they wanted the they met with the president. They convinced him to set up another office of scientific research and development. The National Research Defense Committee was good for studying fundamental issues like this uranium fission, but if you wanted to really build a bomb, build a device, you needed also a technology development committee. So they set up an office. The president set up an office reporting to him, Roosevelt, and Bush became the director of it, and Conant became the director of the National Defense Research Council, which was part of his office. Still, even though they set this up, Bush and Conant just wanted the uranium business to go away. They were convinced it would bear no fruit, it wasn't worth the effort. So unlike the British and the Germans, they just ignored the report of this National Academy Committee and hoped that this all would go away. Progress continued. After Seaborg had discovered plutonium, after he had isolated a small amount of plutonium chemically from neutrons hitting uranium-238, they then put it in the cyclotron, and they discovered that the cross-section for fission by impact of slow neutrons was larger, almost twice as large as for uranium. That was a shock. That it was a better fission source than uranium-235. And so that opened a new direction to make a bomb that you could then make plutonium, separate it, and it could then be what fissions in a bomb. Bush and Conant still were not convinced. A few weeks later, Lawrence did another experiment at Berkeley and found out that the chance of fissioning plutonium goes up a lot. And if you use fast neutrons, which you'd have to do in a bomb device, then it was 10 times better than uranium-235. So then the scientists really got excited about plutonium more than uranium has potential to build a bomb. And so this is Segre, that's Seaborg. Segre also got a Nobel Prize in 1959 for the discovery of the antiproton. So he was another very esteemed physicist in this period from Fermi's lab in Rome, originally. At the same time, Hitler was trying to expand his empire. You know, you'd taken Austria, Czechoslovakia, Poland, had taken the Netherlands, Belgium, France, was bombarding England every night by aircraft, softening them up before an invasion of England. Before he invaded England, he wanted to take Russia, to take the Soviet Union. So June of 41, they started Operation Barbarossa to go into the Soviet Union from different directions. The Ukraine, White Russia, up toward Leningrad. A huge invasion. 4.5 million troops, over 1,800 miles, 600,000 motor vehicles, 750,000 horses, still part of this war effort. And it was the largest, by far the largest offensive by the any military in the history of mankind. And the goal was to quickly take the European part of Russia before, European part of the Soviet Union before they invaded England. And it didn't work. Hitler had his sights set too high. They did advance some. They did move into the farmland. They took Ukraine. So they did make advances, but when they tried to get up and take Moscow, they were rebuffed. And they tried several times to take Moscow and could never do it. And so Hitler was too bold in his attempts. So it was huge cost of lives and resources by Nazi Germany to try and take the Soviet Union. It didn't work. The Brits knew the Germans were coming. The Battle of Britain went on until spring of 41. They thought that there'd be an invasion at any time. Charles Lauridsen was a physicist from Caltech. He then went sent to England to assess where the British stood. The British were convinced that you could build an atomic bomb based upon uranium-235. You had to separate it, you had to enrich it, and they were convinced that somebody could build a gaseous diffusion plant that would enable enough enrichment of uranium-235 to get a few pounds, perhaps 50 pounds of uranium-235 per bomb. And finally, that summer, Bush got a draft of the report from the British committee saying that you could, maybe with 25 pounds of uranium-235, you could build a bomb. That you could build a diffusion plant to enrich a kilogram per day. It cost 5 million pounds to do this massive effort. That this could be done by 1943. Not 45 or later, but you could do this by 43. And that this weapon is needed for sure for future wars, but maybe even the current war. And that England should work with the US to do this huge gaseous diffusion plant, this huge uranium enrichment. It's more than they felt they could do in the UK. They were under attack. Same thing happened though. Vannevar Bush got this report, this detailed report from the British committee, put it in the safe, and tried to make the problem go away. So it's amazing to me that eventually the US did get involved, but it took a long time for the US government to really take this seriously. Okay, so